Welcome back, everyone. So I'll continue from where we left off. And of course, needless to say, you can stop me at any time if something is unclear and needs more discussing. Okay. So yesterday we were trying to basically introduce Fluke eigenstate thermalization hypothesis, Fluke ETH in short, and we stopped at a particular point. And let me just sort of refresh our memories by just writing a couple of equations for that. Okay. So so we actually saw the following, that in the Fluke case, the relevant object to look at is this Fluke unitary, right? And basically, that's some object which looks like, which looks like this. This looks like this, and you need this time ordering here because the Hamiltonian operator may not commute at different instances of time, okay? And of course, we also know that if the Hamiltonian is time independent, then this has a simpler form. It just looks like this, right? It just looks like this for an undriven problem. And this thing, this object, can of course be always expressed in the following way, right? Because there's a unitary matrix, so I can express it as an exponential of some Hermitian operator. And this Hermitian operator is what is known as, this object is what is known as the Fluke Hamiltonian. But yesterday we saw that this Fluke Hamiltonian is not strictly a well-defined object, right? Good. So just like in undriven systems where eigenstates play an important role, if you're looking at the stroboscopic dynamics of the system, so just to refresh our memories on that, so suppose we start the system in some reasonably simple state like this, and then I just look at the wave function at specific intervals of time, n equal to 0, 1, 2, 3, 3, and so on, where this capital T is of course the time period of your external driving, then you can see that there is some superficial similarity to a undriven system, right? To an undriven system, okay? But I say superficial, and we already discussed some parts of this because there is an important difference. In the undriven problem, the energy is a conserved quantity, whereas in a Fluke problem, energy is not a conserved quantity. So that's a huge difference, okay? Good. However, we can always look at the eigenfunctions and eigenvalues of this unitary operator, right? And then we can look at local observables and write its matrix elements in that eigenbasis, right? If we do that, then for Fluke ETH, we get the following. So I hope you remember this notation and I don't need to expand on this, right? So M is okay, so this is just some object like this, right? Where M and N are eigenstates of this operator, okay? So this guy, statistically speaking, has the following form for a large enough system. Whereas for an undriven system, so this is Fluke ETH, whereas for an undriven system, you'll get standard ETH. this thing looks like this. By 2, and then okay, this is how it looks like for an undriven system. We even wrote down the result for what happens in a random matrix. And what happens in a random matrix is the following. Okay, where these RMNs were pseudo-random numbers which basically had zero mean and unit variance and could be imagined as being picked up from like a random process described by a normal distribution. Okay, good. So as we already pointed out in the last lecture, if you just stare at these equations, one thing is evident here, that there is energy here in the undriven thing or in the ETH, because energy is of course a conserved quantity, whereas there is no energy coming here in the Fluke problem. But that makes complete sense because energy is not a conserved quantity anymore, right? So the way this generalizes here is you want to remove energy out of the picture. So the easiest way to imagine that is the way energy comes here is you basically think of some canonical distribution. So if you put beta equal to 0, energy goes out of the window. So, and that's nothing but this object. This is just the infinite temperature value of this operator, right? And even here, energy goes out of the window because there's no explicit dependence on this average energy, on this f function now, okay, right? But what I also pointed out yesterday was, at least to the best of my knowledge, while there are several nice works on understanding off-diagonal ETH in undriven systems, this object, the same kind of an object in driven systems, in Fluke systems, is not so well explored. And you can also ask the question that, okay, this thing resembles this thing in random matrix theory. In what limit does this thing resemble this thing in a Fluke problem? Okay, and maybe it'll start resembling this thing when you take this limit. So omega d is just 2 pi by t. So this is a question mark here. Okay, good. So we were roughly at this point. Okay. Oh, sorry. So I must have. Yeah, of course, you're right. There's a square root. Yeah, because, yeah, sorry. Thank you for that. Yes. Yeah, so this is the correct equation. Yes. Good. So I also mentioned this sort of computer test here, which I took from this nice paper by Kim, Ikeda, and Hughes, and I gave the explicit reference to you guys. And basically, we saw that if you just concern yourself with the diagonal part here, let's just discuss that for a moment. So while in undriven systems, if you just take some simple operators and look at their expectation value in the eigenstates of the Hamiltonian, there will be some sort of, this is like the thermal answer as a function of temperature. And yesterday, as we sort of discussed, there's a map between temperature and the energy axis here, right? So basically, for a big enough system, there'll be some jitter in the data points, of course, because you're taking a finite size system, but it'll very closely follow the thermal answer, and the data will splay out towards the edges, okay? And if you increase your system size from, let's say, n equal to 10 to n equal to 20, right? then because your Hilbert space increases from 2 raised to the power 10 to 2 raised to the power 20, these fluctuations actually decrease a lot if you go from n equal to 10 to n equal to 20, because these fluctuations are controlled by the size of the Hilbert space, not the size of your physical system. Okay, so that's why, you know, you can actually do ED and still understand a lot here, even though you're just limited to maybe, if you're very smart in doing ED, maybe to system sizes like 28 or something, or of the order 30, not more than that, for spin half systems, right? Okay? So here you can argue, as I stated yesterday in my lecture, here you can actually show it. Here there is no way to prove it. You can just do some hand waving, but I don't want to do it. I'm just stating it as a fact. So yeah. Okay. But by the way, maybe you remember I wrote these two conditions yesterday. So what is the notation here? Okay. Yeah, I stated it, right? So for relaxation, this is very important. So let me just state it again. And these two things should happen together. And this epsilon is of the order of 1 by square root t. These two things should happen together so that some initial state with some energy in an undriven case, after some order 1 time scale, converges to the thermal answer. If you're just looking at local operators, and we of course discussed that if you look at all classes of operators, because it's a pure state, it may not thermalize, but if you just look at the set of local operators, it will thermalize. Okay, so in that paper by K. Maikeda and Hughes, if you just open their paper, you'll see that there's some plots like this. Actually, they did not exactly plot this quantity, but some related quantity. And if you do the corresponding Fluke thing, the entire thing looks completely flat. Okay, which is a signature of, again, the same thing that, you know, you have gone to that thing and you have lost information about the energy, right? So this is Fluke ATH. Good. So as I promised in the last lecture, now I'll give you a quote-unquote justification for why this happens. I say justification within quotes because, again, this is not going to be an analytic proof. I'll just give you some reasonable arguments, and that's where, and then we'll go on to other more explicit calculations. Okay? Good. So the first important thing which we talked about even in the previous lecture was that now if you want to think of energy, because you're actually driving the system, energy is only conserved mod 2 pi by capital T, right? It's in the same sense as if you take a particle in a potential which is periodic, then the momentum is no longer conserved. It's only conserved modulo something, right? It's in the same sense, okay? Because of that, so it's the statement that if you look at the Fluke eigenenergy values, you can shift any eigenenergy value by this amount, right? It's the same statement that we talked about yesterday, right? So one way of actually thinking about that is you can, whenever you calculate some Fluke energy, you can just put or fold all the Fluke energies in some Brillouin zone, right? That's one way of doing it, right? So you just take care of the fact that it's some periodic variable, okay? So there is already this energy scale in your problem. There's already one energy scale present in your problem, and that energy scale is 2 pi by capital T. That's related to this folding, okay? And this you can control, right? Because suppose you choose a process, and that process has a certain periodicity in time, you can vary that, and so this number would vary, okay? So that's one energy scale that is present to you. Okay, what is the second energy scale? Second energy scale that is present to you is, of course, the total bandwidth of the system. So you have, let's say you have an undriven system. So then in an undriven system, there's an E minimum and there's an E maximum. And for the classes of system we were talking about, which had finite Hilbert spaces at each site, basically the separation between these two is order n, where n is the number of degrees of freedom in the system. Okay? Good. Now, let's imagine the following situation. So this is an undriven system. It's not necessarily non-interacting, it's just undriven. So let's say it's described by H naught. And let's say I make it a Fluke problem by adding a term like this to it, and this term has some structure like this, right? So then suppose you imagine doing just perturbation theory in V, even though I'm not assuming anything about this V being small again, but let's say you just imagine doing some perturbation theory here, then of course, here there are many states, right? There's a many-body problem. So because this is a periodic drive, here what will happen is that you will in fact start coupling states which are separated in this energy, right? This is basically how you even think of Fermi golden rule, for example, right? Because, I mean, if this has a certain periodicity, there is a natural frequency here, and then you can just couple states which have energies separated by any integer multiple of this amount, and then those states will hybridize with each other, right? That's exactly what is going to happen. Okay, good. So now, think of the following thing. Here I can couple states which are separated by 2 pi by capital T, right? That's some finite number. But this thing is a order n number. So if I increase my system size, this thing increases tremendously, whereas this thing stays whatever it is, right? So if you think about it pictorially, there are lots of states here, and this is sort of the spectrum of H naught. So let's say you start with some, let me use some different color. Let's say you start with some state here. This will of course hybridize with some state which is H omega d away from it, which will again hybridize with a state which is H omega d again away from it, and so on, right? So I'm just drawing a very schematic diagram, right? So all these states would couple to each other, right, when you periodically drive the system. Now comes the important point. If you look at the density of states of H naught, this is after all a many-body system. So suppose you look at the density of states of H naught, then the density of states on general grounds would have the following form.
Emax and Emin will also shift, right?
Yeah, of course. They'll also shift, of course. And they'll shift in such a way that the spacing between them would be order n. Yes. Yeah. They'll both shift. Okay. So now suppose you look at density of states for this H naught. So in fact, I'm not plotting density of states, but log of that, because the density of states is a very rapidly peaked function, so it's better to plot the log of it. It's the same reason that when you define entropy, you take log of omega and not omega, right? So, so you just do this. Let's say there's some one-dimensional system, so I just normalize this, and this is energy per site times the system size, right? This density of states will sort of look like this. And it will have a maximum at a place which is associated to a certain temperature. What is that temperature? This is just from statistical mechanics. I mean, what is that temperature called? Sorry? Infinite temperature, yeah, so that's correct. And because I have drawn log of rho here, if I shift anywhere away from infinite temperature on either side, actually the number of states there is exponentially smaller than the number of states here. right? I hope that makes sense to you. So then, just from this pure statistical argument, when you're superposing these states here like this, then the dominant contribution is going to come from the middle of the spectrum. I hope you see this logic. This is, of course, a hand-wavy logic, but you're just adding lots of states and they're hybridizing with each other when you're putting a periodic drive here. But the maximum number of states really lie here, right? So when you think of this hybridization, the properties of these wave functions are going to be dominated by states which lie in the middle of the spectrum. Okay, no matter where you start with. You could have started here, or you could have started here, or you could have started here, right? So in that sense, all the eigenstates of the Fluke Hamiltonian should mimic completely random infinite temperature states, just from this statistical argument. Okay, so this is one argument. I hope this makes sense. Okay, this is just a statistical argument because there are so many more states here than here or here or here or here. Okay? Good. So that's one rationalization of why ETH becomes Fluke ETH when you introduce a periodic structure to the Hamiltonian. Okay? That's one argument.
And because the states are very closely spaced, that this prefactor doesn't depend on the energy.
Which prefactor?
In this ETH, you have a term that doesn't depend on the prefactor. You have a prefactor that doesn't depend on energy.
Oh yeah, I'm just talking of diagonal ETH here, right? So this argument suggests this argument. So I'm just calling it a suggestive argument because I'm not proven anything. See, this is clear that suppose you start with this state, this will superpose with this, and this not superpose, actually hybridize because of this matrix element, but yeah, so these states will get connected, right? And this is some order 1 number, whereas this is an order L number. So you're connecting lots of states. But the dominant number of states would necessarily come from this region, just from statistical arguments, right? So therefore, it's expected that the properties of the resulting state would mimic a infinite temperature state or a completely random state in Hilbert space, right? And if that is true, then of course, if you take an expectation value of a local operator, it will have no dependence on energy, and that's what we see numerically. Okay, so that's one rationalization of this result. Okay. So what is the second way to rationalize this result? The second way to rationalize this result is the following. Of course, please note that I haven't talked anything about off-diagonal Fluke ETH, which I'll mostly avoid during these lectures. Okay. So what is the second way of rationalizing this result? So remember, we drew this graph for the undriven problem. So let's say you take a bunch of initial states and you just let them go, and the initial states share the property that they have the same energy density to start with. Then something like this happens if you wait and order 1 number of time. So you're looking at some time evolution of some local operator, local in real space, and after a particular relaxation time, which is typically order 1, the system actually loses memory of its initial state. It just remembers the energy it had, because the energy in a unitary evolution dictated by this kind of a unitary matrix has a conserved energy. So there's one conservation here. Okay? So it remembers its conserved energy, right? So we saw that. So now if you think in terms of statistical mechanics, if you have a problem in which you have energy as the only conservation law, and then you try to sort of extremize entropy, then naturally you get this kind of a canonical distribution, right? So this kind of a canonical distribution, okay? And this basically implies that energy is actually a conserved quantity here. If you have some other conserved quantity here, let's say some other operator O1, these are important for, let's say, integrable systems, right, which were mentioned a couple of times and also last week, I'm sure. Then you put some other Lagrange multiplier here maybe for the different conserved quantities, right, so on and so on, right. But anyway, in this thing, there's only energy, so you get something like this. Now we are saying that in the Fluke case, even energy conservation is lost. So because energy conservation is lost, now you don't even have that. So your reduced density matrix for a finite patch should basically look like the identity matrix. So what do I mean by that? So again, if you take a big isolated system and you just look at a finite patch here, by finite patch I mean that if you double the system size, you should not double this thing. This thing should stay the same. So that's the notion of finiteness here. Then if you, of course, the full density matrix is whatever this pure wave function is, right? But the reduced density matrix is, as Subroto also mentioned, when you integrate out certain degrees of freedom. So let's say these degrees of freedom are denoted by S bar, and the rest of the degrees of freedom are in S, in region S. Then this reduced density matrix, when you have traced over S bar, actually should go to this guy as T becomes sufficiently long. Time becomes sufficiently long, okay? So even from some simple statistical arguments about lack of any conservation loss, you can see that this thing is the most natural density matrix you can write, but this thing is nothing but tracing over all states in your Hilbert space. So that's what we saw in the diagonal ETH, okay? So that's the second way of rationalizing this result. But I would again like to stress that these are not proofs. So, I mean, just because they seem very plausible arguments may not mean that there's some more interesting physics hidden here and you shouldn't stop thinking about them. So that's all I would want to just add here. Okay? Yeah. Where, sorry? Here? This one, sorry? Oh, okay. I just said that the reduced density matrix of this region in space, which I denote by S, should converge to the identity density matrix or just the identity matrix as your time becomes sufficiently long compared to this order 1 time. That's all. Yeah. In the driven problem. Yeah. Okay. Now I would quickly like to mention one test which I think we also heard the reference to in Subroto's lecture. This thing about the level statistics, repulsion or whatever, I'll just like to mention it for completeness. Maybe it's been discussed already last week, but I won't spend too much time for it. I'll just mention it for, yeah. Oh, okay. So, see, there's this spectrum, right? And this spectrum is the spectrum of some many-body Hamiltonian H naught. Now, let's say I add some V of t to it, and this V of t is a periodic function of time, right? Then your energy conservation is lost. Then if you just want to think perturbatively, then if you have a state of H naught here, then this state can hybridize with another state of H naught, which is separated by H cut omega d, where omega d is just 2 pi by t, right? So this is a periodic function. For example, you see this when you try to derive Fermi-Golden rule, okay? So this state will hybridize with this state will hybridize with this state will hybridize with this state, and so on, right? Now, because there is this hybridization, you can ask where is the maximum contribution coming from which kinds of states in H naught. Then the maximum contribution has to come from this bunch of states here which are living at infinite energy, because the because if you consider the number of states in this energy interval versus the number of states in any other energy interval, there are exponentially many more states here than any other interval. So purely from statistical grounds, if you consider a hybridization like this, where you just keep adding states which are separated by h cut omega d ad infinitum, then that soup has to be dominated by states in the middle here. That's it. That's the argument. I don't need to argue. This is a property of statistical mechanics of, yeah, I mean, this happens, yeah. You can think about it. It, yeah, has to happen.
Periodic driving somehow leads to state and this reduced density matrix in which the states are equally likely because it's an identity. That's what is the...
Yeah, roughly speaking, that's, yeah. Even though, again, okay, really carefully, I won't like to call it an infinite temperature state. I would rather like to say that the system flows into a steady state where if you just look at the diagonal properties, they appear featureless, right? Because actually it doesn't go to an infinite temperature state in the strict sense because there's no notion of temperature here, right? It's actually going to a steady state. And that steady state, if you just look at correlation functions or expectation values, that answer happens to coincide with the infinite temperature.
And in computing that reduced density matrix,
yes.
that identity, I should take care of only those energy states which are in the middle of this?
No. This you can do in general, but of course, as Shubhrata also said, this is a hard calculation. So let's see, how am I doing with time? Not too well, but anyway. So suppose you start with some initial state. Then, given some Fluke problem, like the one which was studied by Kim, Ikeda, and Hughes, right? You can always do this on your computer, right? For, let's say, some system size, and get some wave function after time t. So then, your full density matrix is just this.
No, this part I understand. Then you take
No, then you take the trace over, let's say, so you define a patch in real space which is finite, and then you trace over everything else. That quantity, when this n is sufficiently large, goes to that quantity, okay? Where, of course, what do I mean by sufficiently large? Even in these Fluke systems, there's a notion of relaxation to the steady state. And again, there's some order 1 time. So if this n times t is sufficiently large compared to that order 1 time, then you see this convergence. Yeah. Right. 2 questions. Yeah. Go ahead.
The amortization goes in the up direction, whatever the form of the concrete form of E of t.
Mm-hmm.
I mean, you draw some arrows for the amortization. It's always in the up direction, from lower to higher energy.
Oh, that, yeah, the arrow doesn't really mean anything, but even if you started there, in the top, I mean, you can of course lose a quantum of h cut omega d and then it'll go in the down direction. So yeah, it's invariant to whether I start there or anywhere. Exactly. Oh yeah, that's an important point, yes. So, yeah, that's correct. So basically, not only pumping, but it can lose a quantum of h cut omega d. So even if I started here, I would just keep drawing this. Point is, this is like a fixed point here. I mean, whatever you do will just, yeah. Okay, let me just mention one thing about this level statistics quickly, and then I'll go on. So again, we have heard about these 2 phrases being mentioned, integrable models and non-integrable models, and it's just good to at least point out one test through which you can clarify which is which, unless you have some good theoretical insight into why something should be integrable or non-integrable. Then, so suppose you have some Hamiltonian. So let's say like the kinds of Hamiltonian Subroto was showing, which is basically the same as I was showing because two of the authors were the same in the paper that I also mentioned. So it's like some transverse field Ising chain, but there's also a longitudinal magnetic field, and that makes the problem like a chaotic problem or a non-integrable problem. Okay, so in that problem, of course, energy is a conserved quantity, but suppose you're doing it on a periodic boundary condition, then momentum is also a good quantum number, right? And in some other problem, maybe total spin is a good quantum number or so on, right? So as we know, we use all these conservation laws that we have at our disposal whenever we try to attack a problem through exact diagonalization to block diagonalize our Hamiltonian, right? So basically, there might be a bunch of commuting global symmetries in our problem, and we try to take as many as possible those global commuting symmetries and already put the Hamiltonian in a block diagonal form. This is the usual thing that you always try to do in any exact diagonalization. But it's actually very important to do this even for this level spacing test, because as you might have already heard about, in chaotic problems, there is a notion of level repulsion, which is not present in non-chaotic or integrable problems. But to see this level repulsion manifestly, you have to ensure that you have taken care of all the mutually commuting global symmetries of your problem. Otherwise, it can always happen that there is an eigenstate with some quantum numbers and there's another eigenstate with some other quantum numbers, and they can always cross each other, even in a non-integrable problem, because they have different symmetries, right? In some sense, they are living in two different universes, and yeah, okay? But if you resolve all the symmetries, this cannot generically happen, okay? Good. So suppose you do that, and then you look at your biggest sector. Maybe your biggest sector is the momentum equal to 0 sector, right? So you look at your biggest sector, and then from your exact diagonalization, you get a bunch of energy levels, right? Then this level spacing ratio test is the following. So you calculate the following quantity. So you arrange your data in some increasing order, after taking care of all these subtleties that I mentioned. Otherwise, if you don't take care of these subtleties, you can actually get completely incorrect indicators even in a non-integrable theory. You might think a non-integrable theory is integrable or vice versa. Okay, so you have to take care of this. Okay, sometimes it's subtle. You may not even realize what the symmetries are. Then what you should do is maybe you should put some tiny disorder in your problem, right? So that you understand what I'm saying, so that you at least resolve the more obvious symmetries, right? So anyway, so yeah. So you do this, and then you calculate the following. And this quantity, I'll define what this quantity is, by definition between 0 and 1. And what is this quantity? This quantity is the ratio of two level spacings, two consecutive level spacings. So, sorry, this index is Sn minus 1. So, yeah. So, what is this Sn? Sn is, as I said, the energy difference between two consecutive levels, right? So, you just go up your data file, you keep computing this, you keep taking this ratio. So, this ratio can either be less than 1 or greater than 1. If it's greater than 1, you take its inverse and store it in the data file for this R tilde, right? And you just keep doing it, and that's it. Now, in a big system, you have lots of states, right? So you get a big data file with lots of numbers for R tilde. From that, you can draw a histogram, right? So when you draw the histogram for that, of course, this object is between 0 and 1. So if it's a non-integrable theory, regardless of whether there's Floquet driving here or no Floquet driving, if it's a non-integrable theory, it sort of looks like this. And if it's an integrable theory, it sort of looks like that. And these are two universal functions. I won't go into what those universal functions are. They can be derived. Okay. So the important thing here is for a non-integrable theory, the weight here goes to 0, which signifies level repulsion, whereas for an integrable theory, there's actually a lot of weight here, which signifies the absence of level repulsion. That's the most important thing to take from this graph. Another important thing is if you just calculate this expectation value of r hat from r tilde from here, or just from your data file, then for a non-integrable theory, at least for big systems, it should approach a certain universal number, which to the first two decimal places is 0.53, whereas for an integrable theory, the same number is 0.39 to the first two decimal places. Okay, and this kind of an analysis was very useful in even sort of figuring out when a theory is, let's say, ergodic versus when it's many-body localized as you tune disorder and so on. Okay. And
this is sensitive to this block decomposition, right? I mean,
correct. You need to resolve all the global symmetries, otherwise you'll go wrong.
Which is non-trivial to do, like numerically one.
No, it's not always non-trivial to do. Well, if you have some non-abelian symmetries, it's non-trivial to do. See, I'll give you an example. Suppose you have a problem in which SZ is conserved. Then it's very easy to do, right? You know how from your, what is it called? In your computer, how to label states so that SZ is a good quantum number. But suppose I tell you S square total angular momentum is conserved, then it's a bit more non-trivial, right? So that's the technical challenge. For some symmetries, it's easy. For some others, it's slightly more involved. For momentum also, it's easy. You know how to write plane wave states starting from usual Fock states, right? So, yeah.
This kind of symmetries, do we need to understand just from the Hamiltonian?
Yeah, okay, my short answer is, if you're sufficiently clever, you should be able to understand it from the Hamiltonian, but sometimes a global symmetry may be reasonably complicated. So let's say you resolve all your symmetries and you think your model is non-integrable, but you somehow see that there is a Poissonian level repulsion. Then one issue might be that you have missed some global symmetry which is commuting with the rest of the symmetries that you have taken. That's why I mentioned then what you can try to do is put some small disordering field, right? Because disorder kills many symmetries like translations, rotations, and things like that. It only preserves internal symmetries, disorder, right? So those symmetries are easier to guess many a times. You see what I'm trying to say, right? But of course, I mean, yeah, you need some thought to like classify all the symmetries of a problem.
So basically when you do the numerics and you end up seeing level repulsion,
right,
then you know that you've taken into account all symmetries.
Correct,
so just
correct.
suppose you don't see it.
Exactly, right. And that's why I just made this comment that then you can at least try to put some disordering fields or something. Then at least you rule out some symmetries like translations or rotations, right? So then you just think of like internal objects, internal symmetries. Yeah, but that's correct, yeah. Well, it has happened to me, so I mean, yeah. So then what I did was just put some disordering field, and then later on I realized the symmetry, and then of course everything worked out. So yeah. So.
I had a doubt.
Oh yeah, please.
When you talk about putting the disorder on the system, do you mean that after doing that you don't need to talk about the symmetry and you can diagram?
No. As I said, disorder only removes certain kinds of symmetries. For example, suppose a system has translation symmetry and you put disorder in the couplings, right? I think in one of the slides Subroto showed there was some disorder in all the couplings, right? Or maybe one of the couplings, I don't remember now. So then of course translation symmetry is gone. Similarly, rotational symmetry is gone. But imagine that you're disordering some problem, but there is some other kind of a symmetry which is in some other space, maybe related to rotation of spins in some internal space. Then disorder in real space won't kill it, right?
Yeah, but if you don't know the symmetry before, and then what do you do for this time?
Nothing, you just do the best you can. No, but that's correct, right? If you don't know something, then yeah, it's a chicken and egg question. If you don't know something, then you don't know it, right? That's it. Then you might be misguided, right? Then you just try to be as careful as you can and hope that you're not misguided. That's it. No, but this is the honest answer. This is true for everything. Yeah. Okay, you don't seem satisfied, but okay. Right. Oh, I've already completed the loop, so I'll go there. I'll switch here. But now, you guys should be a bit disappointed because it seems that, if you wait long enough for these fluke interacting systems, then everything seems to sort of go to a steady state, and that steady state is completely featureless. It just cares about your Hilbert space, but nothing else, right? Because you're tracing over all the states, and that's it, right? So then the real question in the field is, how to see non-trivial examples or whatever, phases of matter or whatever of, sorry. So that's the real question. So there are two perspectives that you can take here. So the way I sort of thought of it here was that fluke ETH is sort of a generalization of usual ETH, right? So even in undriven problems, there are some very interesting cases where ETH is not satisfied. So this is in the undriven problem. So there are some very interesting cases where ETH is not satisfied. Two examples are, there are many examples, but okay, I'll just maybe write them. So one sort of example has already been mentioned, integrable models. Another example which has already been mentioned is many-body localization. A third example, which perhaps I'll have a bit to say more because I don't think it has been discussed so much both in the undriven and the driven context, is many-body quantum scars. And there may be other surprises which we don't understand yet. So when your undriven problem does not satisfy ETH, it is at least plausible that your fluke problem might again escape fluke ETH. It is plausible. It is not guaranteed to happen, but it is at least plausible. Okay, and many a times that happens. So if you go to the corresponding fluke thing, for a class of integrable models, not all integrable models, for a class of integrable models, it may happen that it does not heat up to that trivial steady state. It in fact goes to some more non-trivial thing, which is known as periodic generalized Gibbs ensemble. I'll give an example of that and then it'll become much clearer. Then similarly, if you introduce a fluke structure here in this problem with many-body localization, you might get a very non-trivial phase, which is known as a time crystal. And I'll also discuss that. But I won't, of course, be able to discuss any of these topics in great detail, but hopefully you'll be able to at least get the bare bones of these topics and then read literature on your own, okay? And then, even here, it might happen that you generate what are known as fluke scars. So what that means is that if you look at the eigenspectrum of the fluke unitary, so in this particular case, while most of the eigenstates would look completely random, there might be many special eigenstates which look anything but random vectors in some Hilbert space. Right, so yeah. So that's one class of problems where you can evade this trivial sort of steady state. The other thing is what happens if there is ETH in your undriven problem. Still, you can actually drive the problem in an interesting manner such that the following happens. So imagine you're looking at some local operator and you're looking at this Fluke problem. So let me just put n times t as a time axis. So maybe I'm just looking at it stroboscopically. So maybe something like this can happen. So let's say, so this is 0. So let's say the late time infinite temperature value of this operator is 0, just for convenience. It could have been anything else. Let's say this is 0 for convenience. But what I'm saying is it can happen that when you drive the system periodically, it can show some very interesting pre-thermal physics. So it can show some non-trivial physics in a big time window, and after which it eventually relaxes to this trivial physics. Okay, so of course that is also very interesting, right? So because you can at least access some very non-trivial state of matter for a reasonably large time window, and then ultimately the theory goes on and realizes that it needs to satisfy Fluke ETH, right?
So for this one, I take a model that is known to show ETH, and then I drive it.
Exactly. And again, I hope to give some discussion on this as well, right? So these things are clubbed under pre-thermalization mechanisms. Okay. For example, I hope to discuss at least one example where, so all of you sort of at least know that for stabilizing many-body localization, you really need strong disorder, right? But I'll at least hope to show you an example where you can get a pre-thermal time crystal without any disorder. Okay, so without any disorder. So, yeah. So what is phase transition? You're asking, is there a phase transition? No, I would like to imagine it more as a crossover. Yeah, it's a crossover. But the interesting bit is that something quite non-trivial can happen here. For example, something like a time crystal can emerge here, right? So, yeah. Of course, I haven't told you what a time crystal is, but by now I'm sure everybody knows that it's something non-trivial, right? Because I think it appeared in one episode of Big Bang Theory also, right? So it has to be non-trivial, okay. Or maybe I'm confusing. Maybe magnetic monopoles appeared there, but sorry, yeah. Okay, well, so time crystals must have appeared somewhere else. Okay, anyway, yeah. Okay, good. Right. So far so good. This is the overview of where we want to go. We want to somehow evade Fluke thermalization. Okay. By the way, when I said that, there is this interesting pre-thermalization physics and we don't understand much of it, part of it is related to the fact that we don't understand off-diagonal Fluke ETH very well, because actually the information about that is also hidden there, right? But so, yeah. Okay, good. But first, in the remaining half an hour today and in my subsequent lecture tomorrow, I'll discuss about the solvable case of Fluke physics, namely, I'll take a transverse field Ising model and I'll periodically drive the magnetic field there. And one thing which this is actually there in many papers, the equilibrium version of it is textbook stuff. The non-equilibrium version of it is not yet perhaps textbook stuff, but it's not terribly complicated, so I'll like to discuss that. One thing that I'll really want to discuss, which is not perhaps explained in one paper, one particular paper in any great detail, but scattered through many papers, is Subroto talked about this concept of entanglement and how it grows as you keep doing unitary dynamics, right? So what that means is, what that roughly means is, suppose you imagine you take a completely unentangled state of spin half degrees of freedom. Maybe you just start with some state like this, all spins with sigma x equal to +1. And let's say you do either some Hamiltonian evolution like that or some unitary fluke dynamics, right? And then the entanglement in the state keeps on increasing with time. And typically it's hard to calculate it analytically. Typically you resolve to numerical things and you cannot go to very big system sizes. But in this theory, you can actually calculate the entanglement entropy in such a way, you can actually set up the problem in such a way that you can then go to your computer and calculate the kinds of plots that he was showing for maybe 10 to the power 5 spins or so on, very easily, right? So I'll try to set up that machinery because it's not completely obvious how you calculate the entanglement entropy here, even from Jordan Wigner. But once you realize it, then it becomes obvious. And then you can go on your computer and just write a small program and see many things emerging in front of your own eyes. So that's the goal. For example, one thing which you should be able to verify is the following. If you take such a kind of a system, right? And I'll of course go to specifics later on. And you look at the entanglement entropy of small l number of consecutive spins. So this word is going to be, this phrase is going to be very important, consecutive spins, okay, from a calculational point of view. Small l adjacent spins. So if I want to look at the entanglement entropy of small l adjacent spins as a function of time, so I plot small l here and I plot S of L. So suppose you're just looking at, you are looking at it stroboscopically as a function of n. So suppose you look at this graph for n equal to 2, maybe, then it looks like this. For n equal to 10, looks like that. Maybe for n equal to 40, sorry, I should. And so on, okay? So an important thing comes up here. So suppose you look at it for n equal to 2. That means you have acted the unitary on it for 2 complete cycles. Then what happens is, what this graph is telling you is that there is a reasonable amount of entropy which has been generated till a certain subsystem size, and after that it's still area law, right? Because the entropy is saturated. This is a, yeah. As you hit more and more unitaries, so let's say 10 of these full unitaries, then you see this length scale has actually increased, right? So your entanglement has spread. So it has increased to some point here. And as you go on, it has increased further, right? And so on. So when we end the discussion on the transverse field Ising model, I'll give you a setup where you have to again go to the computer and program it. But it's a relatively straightforward code to write, and you can go to very big system sizes and actually calculate these kinds of things, okay? So
at a given L, if as the more the number of driving periods are applied to it, the more is the entropy.
Yes.
For a given L, right?
Yes. Yes. Right. And actually, ultimately, if you really wait asymptotically long, this thing will go to a non-area law curve. If you have like an infinite system so that I can really do these things and not worry about boundary effects, then yeah, that's, yeah. Okay, so let me just start with how to get this. So, okay. Most of you may be familiar with Jordan-Wigner transformation, but I'll just at least jot down the main points here for completeness, and then you can refer to various textbooks and work out some of the missing steps, right? But when it comes to this calculation, how to calculate it from Jordan-Wigner transformation, we'll discuss that in a bit more detail because, yeah, as I said, most textbooks don't explain that. Of course, there are many nice papers which explain that, but yeah, okay. So any questions so far? Okay. Yeah.
In this case where we had this pre-thermal region,
Yes.
do we know to what value it saturates in the pre-thermal region? By some
Oh, yeah, that is dictated by, what that pre-thermal region is. So in different cases, there can be, different types of Fluke Hamiltonians describing that pre-thermal region. And in some cases, like this pre-thermal time crystal, there may not even be a Fluke Hamiltonian describing it. So the short answer to your question is, it's a matter of detail. You need to go to the specific problem and do this calculation there, right? Yeah. Oh, let me just, since you asked, let me just say one more thing here and then I'll go to this example. So the usual pre-thermal thing which people sort of understand very well is something which is known as high frequency driving. So imagine you draw two axes, one is T and one is 1 by A, which you can think of as amplitude of the drive. So people really understand well what happens here. So this is known as high frequency pre-thermalization. I'll briefly state what it is later. So this people understand really well, and here this pre-thermalization time scale is basically exponential of omega d. So it doesn't diverge with system size. It's just some number which is very large, okay? Where omega d is normalized by some energy scale of your system, maybe J or something, right? There is also something which people more or less understand at high amplitudes. So let me put a cut here. Okay, so people roughly understand this region, but there's this entire region which is not well understood. So what I'm trying to say is there might be pre-thermalization mechanisms at not very large frequencies, but moderate to small frequencies, which we just don't understand. So that's another open question in this area. So really, how to think of various pre-thermalization mechanisms in this sort of, if you wish, parameter space, okay? Only understanding that we have, which is a good understanding, is sort of here, here, and in some cases here, where some amplitude is increasing as a function of frequency, driving frequency, but the others are not. So here, here, and on some 45-degree line. But we don't understand the rest of it, okay? So that's another open issue. Good. Yeah.
As I'm increasing this closed-loop time, I see we need larger and larger subsystem size to reach this point saturates. So larger and larger subsystem wave is increasing for different closed-loop time as why this saturation?
Because your entanglement is also increasing. That's the point. Because your entanglement is also increasing. So, sorry, there's no time here, by the way. This is a function of L. Yeah, this is L, right? Yeah, but as your N increases, your entanglement has to increase because you're generating more and more entangled structures in your system. Yeah. So right now there is no time here, right? So anyway, I'll explain this thing. You can see this figure and a corresponding figure where there is time there, just to answer your question. In some paper, I mean, there are many references, but I'll just give one reference of my own. Some phase ref V in 2016, okay? Yeah, so this is panel A of figure 1 there, and your question is related to panel B of figure 1 there, okay? So anyway, Yeah. But let's understand these calculations, then you can do all the calculations yourself and verify everything. Okay, good. Yeah, I won't be able to possibly finish this thing today, but that's okay. I'll take over tomorrow and try to do it. So, transverse field Ising model on a chain. So, basically your Hamiltonian, so your system lives on a line. Okay, and it has spin half degrees of freedom everywhere. And basically the Hamiltonian looks like this. There's a magnetic field which you can make, if you want, as a function of time. Okay, and then there is a term like this. I hope you have all seen this model somewhere, right? So it's a very well-known model. And for concreteness, I assume periodic boundary conditions. So that means if I have a system with L sites, then that means this equation is true, where this alpha signifies x or y or z. Okay, good. Okay, and as I said, you label the sites as 1, 2, 3 till L. Okay. Now, as you already know, the spectrum of this theory, suppose you are not driving it, the spectrum of this theory can be exactly solved using Jordan-Wigner transformation, right? And for concreteness, I am following the notation for Jordan-Wigner transformation as given in Subir Sachdev's textbook. Okay. There's actually a nice SciPost physics lecture notes on the quantumizing chain, and it's titled very provocatively as the quantumizing chain for beginners. It has some nice stuff about Jordan-Wigner transformation and some of its subtleties, which you can look at if you're interested. I'll just write the reference. So it's SciPost Physics lecture notes 82 2024. And as I said, it's called the quantum Ising chain for beginners. Okay, so just to set up notation, and as I said, I follow this textbook's notation. Sometimes different textbooks give slightly different notations, but yeah. So basically, as maybe many of you know, Jordan-Wigner transformation involves somehow mapping these spins to spinless fermions. And then after this transformation is done and dusted, you realize that the fermions are non-interacting. Okay? So what is this mapping? This is the following, where these are creation and annihilation operators for the spinless fermions. And by the way, I'm writing the transformation on a ring, so because I have this periodic boundary condition. So this is a benign mapping, this is a local mapping, right? Because you look at the fermion density at site I, and from that you can read off what is the value of sigma x at that site. But this is a slightly more non-trivial thing, because not only do you see what is happening to Ci dagger and Ci at site I, there is this interesting product multiplying it. So sometimes people call it the string multiplying this thing. And by the way, this string can have only eigenvalues +1 or -1, right? Because the fermion number can only be 0 or 1, right? So you're multiplying a bunch of +1s and -1s, right? And so the end product of this operation can only be a +1 or a -1, right? And whatever that is multiplied by this operator. So basically, you can think of it as you can break a spin into a fermion and a string. Okay, and just to keep a picture in mind, let me just draw it here. So suppose you are looking at the ith site, this guy, and this is I plus 1, and this is I plus 2, and this is I minus 1, I minus 2, and so on. Then this Jordan-Wigner string concerns, let me use a different color, concerns these bunch of spins. Okay? So that's where this non-local aspect of this transformation enters, right? Because suppose you imagine a very big system, then the string, depending on where you are, can be extremely long, right? So, so even though this is a unitary transformation, there is this non-local aspect here, but that is needed simply because you're trying to map a problem of spins to a problem of fermions. Spins have a different algebra than fermions, right? So it's sort of obvious that you cannot locally represent, you cannot locally map this problem to this problem. So that's where this thing comes as a savior. Okay, good. One more thing that is good to remember here is that what is the vacuum of these C fermions? In terms of the spins, in terms of the real physical degrees of freedom. After all, the spins are the real physical degrees of freedom. So I denote that vacuum by 0, and that is the state this, where sigma ix is +1 for all I. Okay? So this is the vacuum for the C fermion. So it's a very simple state, right? All spins polarized in the x direction. Now, as I said, I'll skip many steps because I want to get to the meat of it. And anyway, this is really textbook stuff. If you see, for example, Sachdev's textbook, or for much more details that Saipo's paper that I have indicated, you can fill out the missing steps if you already don't know of it. So if you take this transformation and plug it in that Hamiltonian, okay, for simplicity right now, let me suppress the time dependence on G. I'll later on just put it back. It's very straightforward. So if you do that, then that Hamiltonian becomes so remember there are L sites now on a ring. So you'll see that there will be an interesting boundary term which will come up, and so there's some hopping of fermions, and there's some pair creation and pair annihilation term, right? But these are still free fermions, right? So. And then there's an extra term. If you do the algebra really carefully, you'll see that this term is, it couples the n spins. Okay, that's that, right? Because since you're on a ring, there is a coupling between L and 1, right? Since you're on the ring. Okay, now what is this NF here? This NF, if you work this thing out, is fermion parity. So what do I mean by this? So you stare at this Hamiltonian. In this Hamiltonian, there is a usual fermion number term, right? There's some fermion hopping term, but there's also a term which creates two fermions on consecutive sites or annihilates two fermions on consecutive sites. So the fermion number is not conserved, right? Because there's this term here. But what is conserved is if you start with a system with an even number of fermions, it will stay even because you can at best create 2 fermions or destroy 2 fermions, right? So if you start with 2 fermions, you can maybe go to 0 or 4, and from 4 you can go to 6 and so on. And if you start with an odd number of fermions, it will always stay odd. So that's the fermion parity here, the evenness or the oddness of the fermion number. That's a conserved quantity here. Okay. Now, one thing which you can try to understand yourself or read these references is, if you take a finite chain like this on a periodic, like on a ring, and if you solve for the ground state at any coupling G, for G tending to infinity, it's very easy because this is the ground state. But if you solve for the ground state at any coupling G and calculate its fermion parity, it turns out to be an even parity. Okay, so that is something which you can try to understand. So basically, at any G, the ground state has even parity. Okay. At G tending to infinity, it's very simple to see, right? Because it's this state, and that's just the vacuum of fermions, so of course it has even parity. Okay, good. Now suppose I'm only thinking of situations where either I'll start with this state, or I'll do either a quench or a periodic driving from some other ground state at some other coupling. Okay, so just to be very specific, maybe I initialize my system or prepare my system in the ground state of this Hamiltonian when the ground state is, when the coupling is some G1, and then I make G a function of time. That's one possibility, right? Or maybe I just make G a function of time and start with this state, right? Whatever it is, I do this song and dance so that I'm just concerned about states with even parity, right? So I'll restrict myself to this class of states further. Okay. So then, because you have even parity here, okay, you can put this thing to 1, okay, and then you can show that the periodic boundary conditions for spins actually naturally implies this equation for fermions. So what did I do? I restricted myself to even NF, okay, and then I get this. Again, this is textbook stuff which is mentioned when people get equilibrium phase diagrams, right? So, so this is basically anti-periodic boundary condition for the fermions. Good. Then of course the natural thing to do is to take this problem and go to momentum space, right? Because it's a non-interacting theory. So we'll do that. So I'll insert, in fact, some extra phase factors in my definition, and they'll be convenient. So these are just some constants I'll put. But so I'll carefully write this transformation. So I'm going to momentum space now. These are, of course, the site indices, which run from 1 to L. So this is the transformation that I do. And let me be completely explicit, because I said I'll give you enough detail so that you can literally compute the thing, right? So I'll give you all the necessary details, right? So this K is 2 pi m by L, where, so let me just erase this. Where this m are these integers. Oh, sorry, half integers. They're actually half integers. Okay. Good. now we are almost there. At least I'll be able to set up the problem, and then maybe in the next lecture I'll discuss how to calculate entanglement from there. That's still a bit non-trivial. Okay, but let me at least set up the problem.
L is even.
L is even. Yeah. So as Shamik said, for these purposes, L is even. Okay, so you put those transformations in your, you just transform your original Hamiltonian with Ci's and Ci daggers to a Hamiltonian with Ck's and Ck daggers. But I have given you the exact transformation, so you can work it out. When you work it out, it gets a very nice form. By the way, so you can see that for each minus k there in momentum, there is a corresponding plus k, and there's no 0 here. Okay, so for example, for minus half, there is half, and similarly for minus L minus 1 by 2, there is L minus 1 by 2, right? So there is a unique k and a minus k here. So I can write the thing just by summing over k greater than 0, like this, where this h of k looks like this. C dagger k, Ck minus C minus k, C dagger minus k, plus 2 sine k, C minus k, Ck plus C dagger k, C dagger minus k. So it's a bunch of non-interacting problems in momentum space. Now there's a further nice structure here because I restricted myself to even NF. So I'll just point out that structure and maybe I'll stop for today and continue tomorrow. So the structure that will emerge is, remember we started with a physical, we started with the physical description which had spin half degrees of freedom. Then we went to fermions. Now I'll show that if you just restrict to even NF, which we have done, and I'll use that property further, you can easily go to a space of pseudo spins which are completely decoupled in momentum space, and each pseudo spin is a spin half object, and they are just sort of doing their own dynamics. Okay, but these pseudo spins are completely distinct from the original spins, right? But let's just derive that, and then I'll stop for today, and in the next lecture I'll see how to calculate entanglement from there, because this is not obvious, right? We want to calculate entanglement in the basis of physical spins, as Shubhrato pointed out, right? But I have done some weird transformations and I have mapped this problem to a problem of pseudo spins in momentum space. But I'm interested in the entanglement of L consecutive spins, L consecutive physical spins in physical real space, right? So that map is not still obvious, right? So let's just do the obvious thing and we'll stop for today. So I get this. And once I explain the entanglement calculation to you tomorrow, you'll see that how to easily generate curves like this, okay? Of course, you still have to face the indignity of numerics, but you can do numerics for some incredibly large sizes here. Right? So since NF is even, here comes the key point. So either you look at states where k and minus k are occupied together, or k and minus k are both unoccupied, right? Because there's even parity, right? So basically I denote k minus k being occupied together as an up spin, because I already told you it's a pseudo-spin representation, so there is a sz equal to up or plus half, and there's a sz equal to minus half, right? So this is my up spin. And of course this in the fermionic language is just this state, and there's a downspin, which is just the vacuum of fermions. No fermions there. If you hit this Hamiltonian, this above Hamiltonian here, if you just express this above Hamiltonian in this basis, it's some 2 cross 2 matrix, you will be able to show that that 2 cross 2 matrix can be written just by using Pauli matrices, and that 2 cross 2 matrix literally looks like this. Good. So we have reduced our original problem to a bunch of, again, spin half degrees of freedom. But these spin half degrees of freedom are pseudo spins, and they live in momentum space, and they're related by a very non-local map to the real physical spins. No, that's it. This guy is the off-diagonal piece. That is related to this term, and no, there's no other term. Yeah. There's a diagonal, so when you write this Hamiltonian in this basis, you'll generate a 2 cross 2 matrix. You'll have 2 diagonal entries and 2 off-diagonal entries. The 2 diagonal entries would differ in sign. One will be a plus epsilon, one will be a minus epsilon, and that can be represented by this. The 2 off-diagonal entries would be identical, and that can be represented by this. So you just need these 2 Pauli matrices.
But the mapping should be right, there should be tau kx, and tau is.
No, it's not a question of thought. When you do it, you get some answer. So then whatever you think, it doesn't matter. It's the answer, right? Yeah. Okay, maybe it's a good point to stop. Yeah, I'll do the rest in the next lecture. So of course, if you have any questions, I can take them.
Why did you take the phase factor?
Yeah, well, if you don't take that phase factor, you will get some factors like I and all hanging. It's not so necessary. You will just then be, you will probably get a tau y there instead of a tau x. But that's it. I mean, I just wanted an explicitly real thing, that's all. But yeah, there's no great necessity for it. You'll get tau y, which is 0 I minus I 0, right? So sorry, off diagonal pieces are I and minus I, right? So yeah.
So, are there any questions? If not, so let us thank Arnab and we'll meet you after lunch.